All right, let's go. Here's our outline for today. And hold on a second, let me turn the lights down just a little bit. Okay, that's better. Quotation from Nicholas Copernicus today. The earth together with its surrounding waters must in fact have such a shape as its shadow reveals, for it eclipses the moon with the arc of a perfect circle, which you don't need a telescope. You can see a lunar eclipse with your naked eye, and there have been a couple in the last year or two that have been visible here from Orlando, so it's kind of cool. What we're going to do today is talk about, to start with, just a few constellations that are handy to know, especially for this class. We're going to talk a little bit more about spectra, and we're going to start with some clicker questions about spectra. Then we're going to finish up with the beginning of our discussion of Kepler's law, and we'll finish that and keep going in lecture on Thursday. The main material about spectra is chapter 5, Light the Cosmic Messenger. The information about Kepler's law is for Thursday is going to be chapter 4. And the chapter about Kepler's law that we're going to talk about today, I believe, is chapter 3. And I have page references in here, so let's get to it. This is old news here. Let's get through this stuff here. Forgot to remove this slide. Our TA has not shown up yet, so I don't know if he's coming up. Okay, here we go. I want to go over the clicker registration procedure just one more time in case you're messing it up or something. The way to do it is to go to web courses and click on this tab up here in the upper left, the iClicker tab. That will take you to this page. And in this page, you type in, sorry, this is not supposed to be up there. Boy. You type in your serial number here, and as soon as you hit the register button, it'll feed back, say you're registered, and it'll say your clicker number, and I believe does it say your name as well? Just your iClicker number? Okay. The reason I don't know is because I can't get this to work in web courses in the normal manner. It doesn't. My phony student or my demo student account doesn't work like your guys' account in all aspects. And this is one, in other words, I can't register my iClicker the way you guys can. Anyways, when you do that, you'll get points, bonus points. And the bonus points are here at the top of your grades page. And you'll get one for today if you're registered for class today. And hopefully you got one last Friday. And there'll be another one Thursday. And then next Tuesday, a week from today, is the first official day of clicking. So that's your deadline to get your iClicker. Now, usually we don't ask too many questions per day. So if you miss 1 or 2 days per lecture, 1 or 2 lectures per semester, you're okay. You have to make the 85% level. But do try to get it done as quickly as you can. I know some of you get not taking the cleaners, but kind of left hanging out to dry by financial aid. They're notorious for not being ultra fast about everything. If that's your case, let me know, and I'll talk to you about it. Questions about iClickers and stuff? Yes. Drew. Repeat. I don't know. What did I do for today? We're still on AA. Actually, we did AA last time. It worked okay. Let's just stay on AA. May as well. And let's keep going. Okay, another thing I want to mention to you, when you're putting a discussion thread together in discussions, which is a good place to ask questions that on any topic except for your specific grades. Now, we don't really have any grades on the books hardly at all right now, but privacy-wise, you can't put your, like your exam grade or anything like that. But other than that, if you have a question about what's happening in class, when something is due, how something works, what page it's on, that kind of thing, post a question in discussions. And when you do that, do me a favor and click where it says allow threaded replies. And that'll keep, if it becomes a really long thread, it'll keep it organized and you can read it really efficiently. The other thing that you can do is down here, allow liking, which I'm not sure how useful that is in web courses, but may as well do it. Let's see how it works. It's kind of new last semester, so try to remember how to do that when you're posted a discussion thread. All right, question?
If you're already registered for another class with your iClicker, for example, if it's DA, how would you change it to be AA?
Okay, good question. If your clicker, you had that earlier this morning?
Well, I'm trying to mix it now. Do you have to do it online?
No, you don't have to do it. Your other class is what I meant.
Oh, it was from last semester.
Oh, last semester? If you had, and it happens, it can happen for a class earlier in the day. No matter what class you're in, if you want to set your frequency to AA, you hold the power button down for a second, and you get a flashing square, and then you type in AA, and then you'll get a message, go nitro. Got it? Okay. And then it'll say ready, and then you're ready to go. Another question? Yeah. 26th, yeah.
26th.
Yeah.
So does that
oh,
mean that for these days that we're using it, what is like a practice?
These days that we're using it, I'm not scoring. We have regular astronomy questions today. We don't have a Chuck Norris question, but everybody's getting a bonus point for participating today. So if you don't have your clicker today, it doesn't hurt your semester grade. It can only help. As a bonus point. But next Tuesday, a week from today, it will go in as part of your 25 out of 25 for class participation. Okay, so that's the official start of that. Another question? Yeah, go ahead.
When we do start actually having to have the clickers in class, do we have to get the clickers right to get the points?
Dude, it's participation. All right? Yeah, it's good. We may as well make sure it's clear. The question was, do we have to get it right to get 25 out of 25? The answer to that is no. You have to participate, whether you get it right or wrong. I keep track of how many you answer, and that goes into your participation grade. So if you answer 85% of all my questions by the end of the semester, 25 out of 25. Okay. Now, I also give, I guess it's not in the syllabus, but it's tradition. You might want to put this in your notes, first note of the day. I give a 4 bonus points reward for iClicker performance. In other words, if you get the questions correct. Now, the performance level that you have to make is 75% correct. If by the end of the semester you've answered 75% of the questions correctly that I ask, then I give you 4 bonus points. And just think of them as being tacked onto your final exam score ahead of time. So 4 points, easier, on your final exam type of thing. Okay, but we won't know that until the end of the semester. So just try to, that's my way of rewarding you for trying your best instead of just clicking B, 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 for every question that I ask, which you could certainly do. It would signify that you're present and participating, but not that you're really thinking very much. And that's what I want you to do. Okay, one last question. Oh, I was going to tell you guys about that. You can't get in. You can't. Okay, raise your hand if you, the question was about how do we get into masteringastronomy.com. Raise your hand if you had a big disaster trying to get into masteringastronomy.com. Yeah, see, that's, raise your hand. Okay, raise your hand if you had a big disaster, but you figured it out. Ooh, it's only people. So I guess you have to be on this side of the room in order to have the brainwave. What did you find out?
Well, I accidentally bought 2 different books because I thought about the wrong book.
Oh,
I didn't buy the wrong book. And then I honestly don't know how I figured it out. I just let me in.
dude, who figured it out? Who knows what's happening? In the back, do you know what's happening with the light blue shirt?
Yeah, identify the access code.
For masteringastronomy.com?
Yes.
Yeah, that's true, but even people that bought the access code couldn't get in, and that's not supposed to happen. Drew, what did you find?
Like, so I got the textbook from like the blind bookstore on campus, and then they gave the access code with it, and you have to like set up like a Pearson account, and you use like the little code, and they start asking you like multiple questions to see like how ready you are. And if you already have an account, it's like pretty easy. I kind of had one, so it took me like 5 minutes. But like, I want to say the hardest part would probably be establishing an account for the website if you don't have it.
Account for Pearson.com. Yeah.
So we have to buy the access code?
You to have mastering it. I don't know. I have a.
Some like come like individually.
Yeah. The problem is the bookstore gives you several different ways to buy it, and plus you can buy stuff online. So right from Pearson.com. The bookstore has a bundle. Did you buy that? Okay. You buy the bundle. Yeah. Okay. So you buy the bundle, and you get the textbook, and then you get a little card or something. What is it? Like a little card type thing? All right. Yeah, and it's got a little scratch-off code or whatever. And you type that in, and that gets you into. Are you on masteringastronomy.com? All right. But the problem is that some of you have bought the masteringastronomy.com access through masteringastronomy.com and got hornswoggled. And that is not supposed to happen. So for those of you that have that problem, all right, we're going to do a discussion thread. I want one of you in class today or after class to start a thread. How do I master masteringastronomy.com or something like that? Make sure it's threaded, and then ask your question. And then you guys that have already gotten in, please do them a favor, look through it, and see if you can give them tips. And in addition, I'm going to give you a tip in that thread. The textbook representative emailed me last night, and I was going to put it in the PowerPoint, but I forgot. She told me that you guys can email her with your name and stuff, and email address and whatnot, and she'll try to look it up and see what the problem is. There's supposed to be a helpline, but I don't even know if they were open yesterday. Everything was, a lot of places were closed yesterday. But I'm going to post that on your thread. So whoever starts that thread, I'm going to post the textbook rep's email and what she told me for you guys to email her with, and then just see if we can get it cooking. And if it becomes a bodacious problem, I'll extend. This first assignment in masteringastronomy.com, it's not really astronomy, it's how masteringastronomy.com works. So it's not like you're missing out a lot of astronomy concepts. But tonight's homework will be, and if need be, I'll extend both of them till like next Tuesday or something. But we want to try to get it, rolling on the normal frequency here. Oh, also, for those of you that rolled into class, you got the registrar put you in the section on Friday, but you didn't get into web courses till Saturday. I extended homework assignment 1. That's the attendance quiz, and you can hack through that. It's open until the end of the semester, and they're basically what they're doing. So you guys might not realize this, but for that federal government attendance regulation, all they do is they run a program. The system administrators of web courses run a program that looks for every class, for every student, to see if there's clicks from that student. So if you click into the homework, ding, even if you get it all wrong, you're in there, you're participating. So it's kind of like participation, that attendance thing. But a lot of you didn't even get in until Saturday morning, which is after the official deadline. So I don't know how they're going to handle that. But I left them. They told me to leave it open until the end of the semester. So just hopefully it won't slow down your lovely financial aid too much. Anyway, let's talk about astronomy instead of stinking websites. Let's talk about the stars. There is a lovely one. It's one of the bestest constellations to know, Orion. And right now, I was looking at it last night. We got home maybe 8 o'clock. And it was up, if you know where east is, hopefully you know how to, the side of campus that's where the sun comes up. If you look in that direction after supper time, you'll see it climbing over the eastern horizon. And by about 11 o'clock, it's going to be pretty much overhead. And if it's a clear night like we had last night, you should be able to see it. Beautiful. The 3 stars on its belt is the key thing to look for. Now I have some comments about it. This is the diagram. And then here's what it actually looks like out in the sky. And I'm repeating the outline from the previous page. Here's what it actually looks like. Yeah, you can see that. That's not too bad. Right here are the 3 stars. Okay, for some reason it's very distinctive. Now, when you look at it in the early evening, he's going to be on his side. He's going to be on his right side. Okay, so it'll be like this, but rotated this way, and he'll be climbing up over the horizon, kind of like he's climbing up on top of the roof or something like that, climbing over the edge. This is the sword down here. There's actually a huge number of baby stars in there. Here's the diagram, for comparison. And you can look this all up. Orion. I mean, if you look up Orion on the internet, constellation, you're going to find zillions of pictures and diagrams and stuff. Anyways, this is a pretty good one. The first main star is up here, Betelgeuse. That's this one. And that one's close enough. We actually have a picture of the disk. It's not just a point of light. We can actually, with really good telescopes, we can actually see the surface, just barely see some surface features of that one, because it's really big. It's very big and relatively close, Betelgeuse. Next one, Bellatrix. That's the left shoulder. That's over here. And then after that, Rigel. That's down here, the left knee. Okay? And if you haven't learned Orion, once you learn it, you're never going to forget it. It's one of those, kind of like the Big Dipper. Once you learn the Big Dipper, you're good. You can never forget it. And the good thing is Orion is visible from all over the planet pretty much. But the only people that can't see it are people like way up by the North Pole or way down by the South Pole. But other than that, you're going to be able to see it. Yeah, I think that's how it would work. Now, nearby Orion is Sirius, and that is this baby over here. Sirius is the brightest star in the sky, not the brightest object, though. What's the brightest? Sun. The sun, of course, is the brightest. Moon is next. And then after that, Venus. And the stars are pretty, and the other planets are pretty bright too, depending on the conditions. But Sirius, as a star, is the brightest. And that's below and to the left. And then constellation Taurus is above. That's a good one to know. And the Pleiades, that's a cluster of stars. And it's hard to see the Pleiades here in Florida unless it's a good clear night. Now we've been having some good Canadian air blowing through. That's why so many of you are wearing the winter clothes and stuff like that. I can see a lot of people wearing coats and scarves and things. And this kind of weather's nothing for me, but I know for a lot of you guys it is. If the sky's clear, you should be able to see the Pleiades. It's kind of cool. The Seven Sisters. A couple more to know. The Big Dipper, Ursa Major. This one's also visible all year round, although here in Florida it might be difficult to see. This one is what we call a circumpolar constellation. In other words, it's so close to the North Star that it swings. Everything circles the North Star, or it appears to circle the North Star. And this one's so close that, here in Florida, you can almost always see at least part of the Big Dipper, if it's clear. But it's pretty close to the horizon a lot of times, so the misty skies of the horizon make it a little tough sometimes. Last two stars of the Dipper part, the cup of Polaris, or of the Big Dipper, point to Polaris. That's our pole star. In other words, when you're standing right at the North Pole and the Earth is spinning underneath your feet, every direction that you point to is south. And if you look straight up above your head, you'll be looking at the North Star, Polaris, and it will appear not to move. Everything else will appear to move, if that's where you are. And any place on Earth, the stars appear to move around the North Star, every night. But the North Star moves and stuff across the sky as the Earth turns. So it itself is not. It does move. It's not immobile. Okay, so that's a good one to know. Some of the actual stars of the Big Dipper are actually binary stars. And actually, a couple of the stars are double binaries. In other words, there's actually four stars, two pairs of binary stars. And you can make a side note to yourself when we talk about stars in a few weeks. Most stars in the galaxy come in pairs. We're a singleton. We're a one-star system, but most stars are in groups of two or more. Most of them are in groups of two. I don't know why that is, except that conditions are right. There's more than enough for one star, and the universe tends to make them in pairs. Summer constellation. Cygnus the Swan, also known as the Northern Cross. It looks like a cross, and the long arm of the cross, or the down post of the cross, is, if you're thinking of it as a swan, that's the long neck of the swan. And it appears to be flying down the Milky Way. So if you can see the Northern Cross in the summer, it's flying along the Milky Way. Now, the Milky Way is tough to see here in Florida because there's so much water vapor in the air. It gets so hazy. And here in Orlando, we have all the light pollution from Disney and Universal. But if you go not too far to the north of us, if you go up into Ocala National Forest and camp out like I sometimes do, and if it's a clear night, boy, you can see the Milky Way clear as a bell. It's very nice. Now, in Cygnus the Swan is a X-ray emitting black hole. Matter of fact, it's called Cygnus X1, the first X-ray emitter that we ever saw in that constellation, and we think it's a black hole. And as I mentioned, I think the last time, you can't actually see a black hole, but we can see something, we can see a pretty big star orbiting that X-ray emitter. So we can see it on we can see something on X-rays, and we can see something orbiting that thing, and we figure out that it's a black hole, and so we're like 99% sure that that's what it is. Also in Cygnus is Vega, and if you've ever seen that movie Contact with Jodie Foster, and she goes to some alien planet or something and sees her dad, and her dad is like an alien from another planet. And it's kind of hokey, that part, but some of the astronomy part is kind of cool, and that's about the star Vega. And we actually use Vega for a hard reference point for our stellar brightness rating scheme. A matter of fact, the Greeks invented it, and we've now put Vega at the very center of our magnitude scheme for rating the brightness of stars. So it's a pretty important one, and it's up in the summer. You can't see it right now. It's up there. Well, it's up during the day. If you were up in the space station, you could probably see it if you were looking the right direction. But for us right now, it's up during the day, so we can't really see it. Unless you're down like at the bottom of a well or something like that, and the well was pointed in just the right direction. But other than that, you're toast until the summer. Well, that's all right. You can look at Orion. Lots to learn about Orion. Anyway, so that's a few constellations to know, and I recommend that you do some stargazing. When I used to teach out in Montana at Montana State University, I would always take classes like this out on star walks a couple, 3 times during the semester for bonus points and everything like that, just to stargaze. And out there in Montana, oh man, you can see the stars like until the cows come home. It's really great out there. But for you guys, oh, you know what we do have? I forgot to tell you guys this about at the start of the semester. Bonus point opportunity. We do have the UCF observatory, the Robinson Observatory, and they have some actual telescopes. They have a bunch of the smaller ones that are about this big around, and they're considered amateur telescopes. And they have 3 or 4 of those out on the lawn by the observatory. And then up in the observatory itself, they have the big, nice one. And they'll, I'll give you the schedule. They'll have a observing program set, the Astronomy Club. And anybody here can go, and you can actually join the Astronomy Club if you have a notion to. Dude, somebody just dropped their eye clicker and it's all over the place. I could see that. Such a nice gentleman, thank you. Anyway, so the Astronomy Club, yeah. And I'll give you guys a PDF. No, I'll give you guys a link to the schedule, and we'll talk about it from time to time. It's Wednesday nights. So take a look, UCF Astronomy Club. Robinson Observatory. So search like Robinson Observatory site, ucf.edu, and you might be able to find it immediately. Okay, last time we were observing the spectra. Did we do that? Yeah, with the diffraction gratings. And here's a photo of a hydrogen lamp, and we kind of looked at that. I have a clicker question for you. Let's do a clicker question today. Clicker question number 1. Hey, everybody ready? Get your clicker on. Frequency AA. No more slacking. Here's question number 1. Which was the brightest line of the hydrogen spectrum? Hopefully this is easy. And I see people glancing back at their notes. Nice. That is why you take notes. You know what an experiment is? An experiment is fooling around with stuff to see what happens, and you take notes so that you can do it again anytime. That's what an experiment is. And if it's a good experiment, you publish it in a scientific book or article in a journal. But that's what we were doing. We were fooling around with hydrogen. And you guys are now looking back at your observations. 30 seconds to vote. And when you vote multiple choice like this, remember, all you have to do is hit the letter. You don't have to hit the send button. If we type in a number, which you can do on this clicker, then you have to hit send. But for multiple choice, just A, B, C, or D, and I've got it. If you get a check mark, that means I've got it. You can change your mind and send another answer again, and it will record that. It'll record your first and your last. And if all you send is 1, it'll record both of those as your first and as your last. All right, let's see what you guys voted for. Uh-oh. Well, I don't know. Maybe I should give everybody free points for this. You made your own decision. I think it's A. And but you know, if you voted for these other 3, I cannot gainsay that. This is my answer. And as a reinforcement, that is known as the H alpha spectral line. And it's not in this picture. In this picture, we have H beta, the teal colored, the kind of aqua-ish, tealish color, and H gamma. That's the purpley blue one there that you can see. And so the red one in hydrogen, famous line. It's known as the Balmer H alpha, Balmer, after a Swiss scientist that figured it all out, the Balmer series. As a note to you from the textbook, every kind of atom and ion and molecule produces a unique spectral fingerprint. And it could be anywhere in the spectrum. This is a picture of the sun spectrum. And when you look at the sun spectrum, it's kind of a curious looking spectrum. It's a continuous spectrum with kind of bullet holes in it. Okay, there's a gap, and all those gaps in it, all those little black spaces are gaps, missing colors. And that is because those colors are being absorbed in the upper atmosphere. The photosphere of the sun is emitting a continuous spectrum because it is hot. But the upper atmosphere is absorbing some of those colors, and they are absent. This is called an absorption spectrum. So make a note of that. An absorption spectrum has missing colors, the colors that have been absorbed by hydrogen. And I'm guessing that, let's see, I'm guessing maybe this one up here is H alpha, or maybe this big one here, nice and solid. And then there's some blues down here. This one, I don't know, that might not be, maybe this is H beta, you know, the aqua one, or maybe this one here. But an astronomer that figures out a spectroscopist, they nail all these things. And this signifies many elements. In fact, this is where the element helium was discovered. They discovered it in the spectrum of the sun. That's why it's called helium, helios, Greek word for sun. They found lines here. Hey, we can't figure out what this is. There's some lines here. We don't know what And we looked at it here because now we know that there's another element, and it's called helium. They found it in natural gas coming out of the Earth. It's left over from the formation of the sun. And it comes out, with the natural gas that is used to heat homes and so forth. And they filter it out, and we get helium for helium balloons and stuff. And the helium tube that we looked at on Thursday, but this is where they first discovered it. Unaccounted for lines. Somebody was AWOL and they didn't know who it was, but they tracked it down. And that's the element helium. The visible spectrum. Wavelengths. The wavelengths of light. Violet visible light has a wavelength symbol lambda, Greek letter lambda. The wavelength of violet light is 400 nanometers. And for red, it's 700 nanometers. So the short wavelengths are on the left here, violet, and the red is 700. Now, beyond the red is bigger wavelengths, and below the violet is shorter wavelengths like X-rays and stuff. And go ahead and write down that name, Roy G. Biv. It's not a real person, they say, but it's a name that helps you remember the order of the colors in the visible spectrum. Red, orange, yellow, green, blue, indigo, and violet. And I guess indigo is over here somewhere. I don't know. That's the color of blue jeans, indigo. So Roy G. Biv. Now you may be saying to yourself, Dr. B, this is really nice, good, nice, fine, perfect, excellent, nice. But what the heck is a nanometer? I'm glad you asked that. Here's some specs. Millimeter, you've all seen that. That's a thousandth of a meter, 1 mm. That's about the width or the thickness of your ID card, your debit card. A micrometer, millionth of a meter, symbolized with the letters, Greek letter mu. That's this kind of, this left to right Y here. That's the Greek letter mu, lowercase mu. A micrometer is a millionth of a meter, and a human hair is approximately 17 of those, average. Or I think the minimum of a human hair is about 17 micrometers. So maybe 10 micrometers or so, 20. And a nanometer is a billionth of a meter. Now, when you're talking about that, that's another 1,000 times smaller. You're talking about like the radius, approximately the radius of the spirals in DNA. The double helix structure. The helices of DNA, radius is about 1 nanometer. And in general, a nanometer is a good unit for atoms and molecules. Scientific notation, 1 times 10 to the minus 9 meters. And you can look that up, I believe, in the appendix of your textbook. All the scientific notation and what nano means, micro, nano. I think the next one is pico, P-I-C-O, and so on and so forth. I always have to look it up. I remember nano, but the other ones I have to look up. Anyways, you can look that up, and I'll try not to leave you holding the bag when I refer to a picometer or anything like that if I ever have to. All right, so nanometer. Let's do another clicker question on frequency AA. All right. Question number 2 for today. Let's see if you retain the concepts over the space of 3 minutes. Go ahead and vote. 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see if you guys are, yeah, pretty good. Most of you voted for that. Try to remember that. Red is big wavelength, longer wavelength. And violet is short. Violet, 400 nanometers. Red, 700. I remember that. And I hope you guys can remember that as we go through the semester. Question 3. I just gave you the answer about 2 seconds ago. "30 seconds. And hey, you guys, this image is actually from InsideMasteringAstronomy.com, one of the work areas. I might give you something like this for homework. By the way, we're kind of doing skipping around a little bit from chapter 2, a little bit from chapter 5 today. But eventually we'll kind of plow through the rest of the chapters, starting with chapter 6. 5, 4, 3, 2, 1, 0. Let's see if you guys are, yeah, geniuses. 700 for red, 400 for violet. Try to remember that. And here's a concept. From page 111, the material properties of each object, including stars, determine the colors it absorbs or reflects. The light coming from each object, therefore, carries an enormous amount of information. And really what it carries an enormous amount of information about is the electrons. You know, what the electrons are doing, at least in the surface of that particular object, whether it's a beaker of bromine gas, a delicious plate of green jello, or a bunch of stars in the Andromeda galaxy. And it's the electrons that tell the tale. The electrons, as we will learn a little bit this semester, control the spectra. Now, let me ask you another question here with your eye clicker. This one's tough. Think. If you measured a wavelength by using trig, i.e. Pythagorean theorem, etc., and yeah. Come on down here and I'll take a look at it. If you measured a wavelength by using trigonometry, etc., and it was 833, which would this be classified? Let me see what you got. Go ahead and vote. Let's see what you got here.
I had just got it like 10 minutes before class.
Dude, it's got bad batteries in it. You just bought it?
I just bought it 10 minutes ago.
Yeah. Bunch of idiots.
And I tried to switch some batteries with somebody else.
Yeah.
Just went to work.
Go get some. It's okay. Did you register it yet?
I mean, that's what I just.
Oh, you just got it today.
Yeah.
Okay, register it after class. Okay, can you do that?
Yeah.
All right. And then you'll have the bonus point. And these aren't for participation anyways until next Tuesday. So it's good. Get it registered. Get some Duracells in there, and see you on Thursday.
All right, thanks.
Hopefully, click it. Did you see how the other guys are? It's working with the other
I
guys.
seen how
Yeah.
that's working, but
Yeah. Yeah, those batteries. That is pathetic. You just bought it.
yeah, that's what I'm saying.
Unbelievable.
So I gotta buy some new batteries.
Yeah, they joined the club, man. And they failed. This, what's your first name? Navarre?
Neville.
Okay. He just, good. Okay. He just bought his eye clicker and the batteries are already shot. So it's just the eye clickers, when you get it, go get some, everybody, when you buy it, go get some Duracells or Energizers or something. All right, let's see what you guys have got here. Yeah, now look at this. Here's an interesting set of data. Look at this. There's a wide spread of answers. Now, what that means to me is we better do a little bit of talking about this. And here's what you want to think about with this particular question. The wavelength is 833. Now that's bigger than 700. Violet is 400. Red is 700. 833 is even bigger than that. It's even redder than red, and that means that it is infrared. Okay, so infrared is, you can make a note of this, infrared is even longer wavelength than red. Similarly, ultraviolet is shorter wavelength than 400 nanometers violet. Okay, so make a note of that. Now, another IQ test. Let's see how you do on this one. Photosynthetic plants. Now, hopefully you get this correct, but as I was just mentioning, the questions today are, you're not being graded on them. But let's see what you can do here, if you can remember this. This is probably from high school biology class, maybe. You might have learned this. Or maybe physics class. 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what we got here. Aha! Another one. Look at this. Another one with a significant spread, which means it's time to talk. Let's talk it over. You see something that's green because there's light shining on it. And in this room, if I turn out the light, I can't tell what color your clothes are. Okay, now there's a gent over here with a red hoodie on. Go ahead and stand up. Yeah. Dude, you're the only one with a red sweater. Yeah. All right, so very clear as a bell, red. Now, if we turn out the lights, there's no way to tell. I mean, we know what it is now before we turn out the lights. But I mean, if you had never seen him and you just saw him at night, you know, it's just like that saying, all cats are gray at night. And that's because you have to have light that bounces off some of the fabric and then goes into your eyeball. I mean, otherwise you're not seeing it. All right? And that means it has to be reflected, which is why the leaves reflect most of the green light, and they absorb a lot of the red. And here's something interesting you might want to jot down. You can sit down, thanks. And what's your name? Octay. Okay, good. Octay, thank you. Thank you for volunteering your sweatshirt. Here's something that's kind of interesting about green, the color green. Plants are green, photosynthesis. We have oxygen in our atmosphere because of green plants. The human eyeball is mostly made of water. I mean, the part inside the eyeball is water. And here's something kind of interesting about water. Fellas, in the back, I can hear you talking. Don't talk over me. Water in your eye. The color that penetrates water, and water is clear to all the colors. Red goes through, all of Roy G. Biv goes through. But the one that goes through the farthest, the most easily, is green. The color from the sun, the sun emits a continuous spectrum from red all the way through Roy G. Biv to violet, and then ultraviolet, and it also emits a lot of infrared. But all the colors. But the color which most of its energy is emitted in is green. So the human eye is perfectly fitted out to see light from this particular star. And photosynthetic plants, for some reason, say, no, I don't want that. I'm going to reflect that light. They don't absorb it. They reflect it. Now, why is that? I have no idea. But I wonder if any like a biologist that studies plants, I wonder if any biologist that studies plants knows the answer to that. I sure would like to know. Why is it that plants refuse the most abundant light source from our sun, the color green? They make it bounce off. I don't know. Different kinds of spectra. This is what we saw last time, the emission spectrum. Now this is a different kind of an emission spectrum here. I think this is sodium. But if you measure the intensity, you get spikes in the intensity. So this is what your eyeball would see. And then if you have some kind of a photometer or something, this is what your photometer would measure. So it would go up for certain colors and then back down to 0. Okay, so the black areas of the eyeball view correspond to the flat line in the photometer record. So go ahead and make a sketch of this. This is what we were looking at on Thursday last week. We were looking at an emission spectrum. That hydrogen source, the helium and the neon, were emitting specific colors and no others. Now there's a different kind, and we've already seen an example of it, and that is called the absorption spectrum. Here it is. The absorption spectrum, it's like the one we looked at for the sun. There are colors that are missing. So for the same element, those look like bullet holes. Okay, so here's the photometer record here, but there's big dips in it. And so those black areas of the eyeball view are kind of chiseled out of the photometer record. So here's if you look at this here, this kind of curve here, a gentle curve here in which all the little chips are chiseled out, that gentle curve, that's the continuous spectrum. That's Roy G. Biv up there. And then these are the colors that are missing. Now in the sun, that's what we have, because there's an atmosphere above the sun that absorbs a little bit of the colors, or actually quite a few of them. Okay, now here's the third kind of spectrum, continuous spectrum. Okay, a hot thermal light source, like an incandescent bulb. And the sun shows many absorption features. It's a continuous spectrum with a jillion absorption features. Go ahead and write that vocabulary term down, absorption features. We'll actually be using regular astronomy papers published in the journal Nature, published in the journal Science, and that's a vocabulary term that you will see, absorption features or emission features. Okay, this one shows absorption. All right. And a star can show emission and absorption in the same spectrum. Ours mostly shows absorption, right? And other stars can sometimes show emission as well. Now, here's the spectrum of Mars. This is this is figure 516 in your textbook. And I'll probably make some homework about this diagram for you tonight, so you'll be able to look at this in masteringastronomy.com and use the ebook or your regular textbook and look at figure 516, the spectrum of Mars. So Mars has got this kind of continuous spectrum here. This is theoretically what it should be, and then here's what it actually is. Actually, this is kind of a schematic of what it actually is, or an artist's concept. In fact, there's a lot of chiseled out bullet holes here, chiseled out bullet holes here, and some peaks over here. And this is ultraviolet, here's blue, and then here's infrared over here. All right, now this is figure 516. I'm going to show you, and there'll be some homework about this tonight. And so you're going to read about this in chapter 5 before you hit your homework. Now, I'm going to show you some real data, and you can maybe make a sketch of it, but definitely look and use your eyes. And let's look at this data. It's from a comet called Hartley 2. This is a close-up, relatively close-up picture of the nucleus of the comet. And in this diagram, they show that water vapor and ice and CO2 are being emitted from the hot part, the part that's facing the sun. It gets warmed up by sunlight. It's being emitted. How do they know that? This is a black and white image. Okay, so how do they know that it's CO2 and water vapor? This is what they get. Their spectrometer, so they're not looking at it through an eyeball. They've got a little light meter back there, and they're measuring the intensity. Is it bright or is it dark? Okay, so let's look at this. Okay, here's the zero line. Okay, that's no light. That's empty space. All right, and here's a dip. Here's a peak. And they've actually labeled, it's from this paper here from the journal Science, they've actually labeled different molecules, H2O, CO2, and here's the wavelength down here. All right, whoa, my earpiece is falling out. All right, so here's the zero line, and let's try to think about what we got here now. Just so you know, you better make a note of this when you're because I got some clicker questions here for you coming up. 3.5 micrometers is the same as 3,500 nanometers. Okay, so here's a question for you. Are we talking Roy G. Biv in here? What are we? 3,500 nanometer. 3,500 nanometers. What are we talking? Maybe a little visible. No, there's no visible here. Because it goes from 2,500 up to 4,500 nanometers. Okay, so there's no visible here. What do we got?
Infrared?
Yeah, we got infrared. All right, so we're looking at infrared only. So this is false color. You wouldn't be able to see this, but they have the infrared optics up there on this spacecraft looking at Comet Hartley 2. All right, let's do a question. Spectral, dude. Okay, everybody better get this right. This is question, I don't know, 5, I guess. And hey, you guys, this is real data. This is not faked up for a textbook. This is what they publish, the real astronomers publish. And we're going to try to use that when we can. Real numbers instead of, rounding off everything to a whole number and all that kind of stuff. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And I gave you the answer to this about 2 seconds before I gave the question to you, so you better get it right. Better have genius level achievement here. Ooh, some of you got caught napping. You weren't listening. Let's look at these results. Yeah, most of you got it right. 82% is right. The answer is infrared. And for those of you that got it wrong, it's infrared because the wavelength spread is from, you can make a note of this in your notes, from 2,500 nanometers here, that's already infrared, into even bigger wavelengths over here, 4,500 nanometers. So that's even deeper in the infrared. Next question. A brain burner. Comet Hartley 2. Which feature is an absorption feature? Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh-oh. We got some splaining to do. All right, the correct answer is B, ice. And for those of you guys that voted for the others, I forgot to stop it. There we go. Some of you guys changed. Nice. That's all right. We're just doing practice questions today anyways. The idea for this is that an absorption feature on this kind of a chart is a dip or a bullet hole. Okay? And the only dip we really have here is the ice. That corresponds to the presence of ice, H2O ice. Okay, then here's over here, this is the CO2 part. So they're looking at infrared, there's a lot of CO2. By the way, I'm guessing that over here, this wavelength is probably the microwave oven wavelength is probably over there. I should look that up. Because water in a microwave oven reacts to long wavelength. Okay, let's talk about Kepler's 3 laws of planetary motion. And by the way, that stuff that we just talked about, you really want to read as much of Chapter 5 as you possibly can. Right? And we're going to talk some more about Chapter 5 concepts as we go. But for today, that's it. Now I want to talk about Kepler's 3 laws of planetary motion. And to do that, you really have to talk about the rise of science in the West, in the great universities of Europe. And the first guy that developed a heliocentric or sun-centered system was Copernicus. And he was an interesting guy. He was a priest, Catholic priest over in Poland. He was also a medical doctor. And he published his heliocentric calculations and models pretty late in life. In fact, he was on his deathbed when they finally published it. And he was kind of humble and, didn't want to draw a lot of attention to himself. And so he waited a little. So finally somebody says, you better publish this stuff. And he gave his consent to do that. And what he did was he calculated each planet's orbital period around the sun and its relative distance from the sun in terms of the Earth-Sun distance. Now, the Earth-Sun distance, that's from page 62 in the textbook. So there's your page reference. I think it's chapter 2. The Earth-Sun distance, side note, fancy name for it today is the astronomical unit, symbolized capital A, capital U, the AU, the astronomical unit. In other words, 93 million miles, 149 million kilometers, 500 light seconds, roughly, from Earth to Sun. And Kepler didn't know, or Copernicus didn't know that, but they used that as their, in their model, okay, this is 1, this counts for 1, and everything else was, 5.2 or, 0.8 or whatever he had in his paper. Another interesting thing was that he discussed his system with other scholars significantly, and that is something that is also a huge characteristic of science as we know it today. The whole idea of knowing something in the scientific way and establishing it as a fact depends on its scientific objectivity. In other words, everybody can claim that the Earth or that the moon is green cheese. That's easy. But to actually show it and for somebody else to verify it, that's the only way that you can say that you have a scientific fact. And that's what Copernicus was about. In fact, Galileo is the one that really brought it all together. Now, another guy, another astronomer, Copernicus was the first, and then Tycho Brahe, or sometimes you hear it called Tycho Brahe. You got to go to Denmark and ask some Danish guy. He was from Denmark. And he was a naked eye observer. Copernicus was naked eye. Nobody had a telescope till the days of Galileo. But he had a really cool observatory. You can look it up on the internet. And the interesting thing about Tycho Brahe was he made he made an alternate to the heliocentric system. You know, with the sun at the center and all the planets orbiting the sun, and the Earth and the moon has an orbit around the Earth. He had everything. Let's see, how did he have it? His system was the sun orbiting the Earth, so that's geocentric, but all the other planets orbiting the sun. So he was kind of this combo version. Now the Copernicus system was everything orbits the sun. And the ancient Greek version from Aristotle and stuff was everything orbiting the Earth. You know, Plato and those cats. Although some people thought that things orbited the sun back in those days. Here's a picture of Tycho Brahe's observatory. And his whole, this is figure 312. It shows a drawing of his observatory. It's basically a gigantic protractor. And from that, he was able to measure angles and stuff with big precision. And basically, the whole thing that he was trying to get to was, you know, how do we observe more accurately, with more precision? And the Hubble Space Telescope is just, and all our other observatories are just steps in repetition of what Tycho tried to do. He had the best observatory in his day until Galileo. And Galileo had a telescope, and that blew everybody out of the water. So here's a famous picture of one of the shuttles going up to, I guess, to repair the Hubble Space Telescope in 1990. Or maybe this is the launch of the Hubble Space Telescope, I guess. Powerful, powerful telescope. One of the best. A beautiful machine, very reliable. Now, getting back to Kepler. Here's Kepler. And Kepler is the one that really set up the playing field for Galileo and Sir Isaac Newton, especially Newton. He was an assistant of Tycho Brahe, so he had all of Tycho Brahe's data available to him. And he made the decision, or he made the judgment call, that unlike Copernicus, unlike Aristotle and Plato and those guys, that the planets, they don't go on circles, they actually go on ellipses. And it's his key discovery, according to page 63 in your textbook. Now here's a picture of an ellipse. There's a cool diagram of how to draw an ellipse using a pencil and a piece of string and a couple thumbtacks or a couple fingertips. I used to do it in classrooms where we had a chalkboard, but chalkboards are like phone booths. They exist in the past, and we have very few phone booths on campus, if any, and very few chalkboards. And we don't even have a marker board in here, I don't think. Yeah, they don't even have a marker board in here. It's unbelievable. Oh, yeah, look at that. They have a little tiny one over there. Anyways, we could do one over there if you want at some point. Now, what I want you to do tonight for homework, we'll dismiss a little early. For homework, you're going to have some stuff to look at in web courses to get you going on the Stardust mission. We're going to have some stuff in masteringastronomy.com. I also want you to be reading the Kepler, Copernicus, Galileo chapter, which I believe is 2, and also chapter 5, and then attacking the actual homework. All right, so try to get that done ASAP. And if you haven't registered your iClickers, do it right after class. You are dismissed.